Hi, I'm Harish from New York University, and I'm going to be talking about our work, which aims to make it easy to use GPUs for executing spatial queries. Since the past few years, large amounts of spatial data is being collected, and these could be like data from cities or through simulations. And proper analysis of these data can greatly help obtain actionable insight. For example, different kinds of analysis of urban data has enabled domain experts to better understand and frame policies for urban planning. Performing such analysis, however, requires running complex queries over spatial data. While this is easy when the data is small, the amount of data now available to domain experts is continuously growing. Not only is the size of the data large, but due to improved data capture methods, the complexity of the data is also high. For example, the geometries that are now available are highly detailed, which further increases the computational cost of executing spatial queries. And due to this, conventional approaches running on local hardware are often very slow. These are typically the kind of tools that domain experts use, and slow queries make it difficult for them to use exploration tools in their analysis. While powerful clusters can be used to speed up complex spatial queries, domain experts often do not have a CS background, thus making such analysis difficult for them. Our aim in this work is to use GPUs to overcome these limitations. So why GPUs? Modern GPUs are often as powerful as what supercomputers were just a couple of years back. More importantly, such GPUs are now part of commodity hardware accessible to general consumers. Given such computational power, it is therefore not surprising that there has been a lot of work in recent years that try to utilize GPUs for spatial queries. However, almost all of these works tend to use CUDA, which is tied to NVIDIA hardware, thus making it impossible to use it on GPUs from other vendors such as AMD or Intel. These approaches typically port CPU-based approaches to GPUs. The problem with this is that GPUs are primarily built for gaming. And even though general purpose computing has improved on the GPUs in recent times, traditional algorithmic constructs still cannot make optimal use of the parallelization provided by the GPUs. Another shortcoming of existing GPU-based approaches is that they are difficult to port across query types. New implementations are needed even for small changes in the query. So let me give an example for this. Consider a simple spatial selection query that finds all restaurants contained within a query polygon. Here, restaurants are represented using points. Conventional approaches first filter the data using an index and then perform a point and polygon test in the refinement stage for each of the filtered points. While this is fine, what happens if the restaurants are now represented using polygons? The same implementation cannot be used, and you would need a different implementation for this scenario. So our aim in this work is to design a GPU-friendly spatial model in Algebra. Basically, we want the model to be easily represented on the GPU and also have a uniform representation of the data irrespective of the type. Thus allowing the same implementations to work irrespective of the input primitive type. As for the algebra, we want a small set of operators that are optimized for the GPU, and we also want them to be hardware agnostic. Note that our main target is database developers. Basically, we want to make it easy for them to use GPUs and improve query efficiency without affecting the way the user is using the system. The key idea in our approach is to translate spatial queries into drawing operations and thus make use of the computer graphics pipeline. Why will this be effective? GPUs are designed primarily to improve gaming performance. And to do this, common graphics operations are supported natively in the hardware. This allows rendering geometries with millions of points in just a few milliseconds. Also, unlike something like CUDA, which is tied to NVIDIA hardware, the graphics API is common across all hardware. So let's look at how we go about doing this. We represent the data using what we call a canvas, which intuitively is simply the drawing of the data. You can think of it as geometries in the world coordinate space in the graphics pipeline. Formally, it is defined as continuous functions over the Euclidean space, and I would refer you to the paper for more details. Let's look at an example of the point data set, such as the restaurant data that we saw earlier. In this case, the canvas, which is a function, maps all the points at locations of the geometry intersects the space to a matrix. In case of points, only the location of the point is associated with a non-null value. The rest of the space basically maps to a null value. In case of polygons, the entire region covered by the polygon has a valid function mapping. What this allows is that even complex geometries made up of more than one primitive type. So in this example, say a single geometry has not just polygons, but also lines and some points. Even such a complex geometry still has the same representation. So as for the operators, we simply adapt common computer graphics operations. Particularly, we define 5 fundamental operators. These operators are like transformations that move around geometries in space, or blending, which merges two geometries, or masking, which clips geometries based on a mask condition. To show how these operators can help and can actually be translated into spatial queries, let's look at the earlier example of the spatial selection of points again. This query can simply be accomplished by doing a blend followed by a mask. What's essentially happening here is that the query polygon and the points are first blended together, and then a mask is applied based on the query polygon to get the required result. And what is interesting is that the same plan, that the same set of operations can be used even if the input is changed to polygons. So again, it's just that the input and the query polygon are blended and then the mask is applied. To summarize, our model supports both basic primitives such as points, lines, or polygons, and also any combinations of these primitives. And we define 5 basic operators, which we show in the paper is sufficient to realize common spatial queries, such as selections, joins, aggregations, and even KNN queries. While the main focus of this work is to create a theoretical framework to use GPUs for spatial queries, it is also important to show that such a model is practical. And for this purpose, we created a prototype implementation that uses OpenGL as a graphics API, in particular, the rasterization-based graphics pipeline. We focus on selection queries using the blend and mask operators and use the concept of conservative rasterization to ensure the accuracy of the queries. We evaluate the selection of points and the polygonal constraints and examine its performance on a laptop that is equipped with both NVIDIA GPU as well as an Intel integrated GPU. Given that index filtering can be done very efficiently, we focus on the refinement stage, which is the main target of our model. We compare our approach with a traditional GPU baseline as well as a CPU baseline. While as expected, the GPU-based approaches outperform the CPU-based approach, what is interesting is that our approach on the NVIDIA GPU is consistently faster than the GPU baseline. This is again because of the way we make use of the graphics operations to enable efficient processing. What is even more interesting is that the performance on the Intel GPU, which is significantly underpowered compared to the NVIDIA GPU, is still able to keep up with the GPU baseline. And this is still orders of magnitude faster than the multi-CPU approach, which is the best one can achieve using only the CPU. This is especially significant since these GPUs are present even in inexpensive low-end laptops, which clearly beats a high-end CPU. To conclude, I would say that this is just the beginning. There's still a lot of research required to make our model's usage mainstream and to integrate it into existing query optimizers. This includes answering questions on how to integrate this model with the relational and georelational model that is prevalent, developing cost models for query optimization, designing indexes that take advantage of the GPU model, and even looking at various possible implementations for the operators. And with this ambitious goal, I'll end this presentation. Thanks for watching.